Hello and welcome to this lecture. We are in now module 6 and where we are discussing about some of the probability models, and using those standard probability distributions we are trying to solve some of the civil engineering real life problems. And this is our third lecture of this module, and in the earlier two lectures we have seen some of the models, for example that normal distribution, then log normal distribution. And so this lecture we will be taking some more continuous random variables. For example, we will take the gamma distribution, then extreme value distribution, and all this distribution similar to the other engineering or other field of application. In civil engineering area also there are tremendous application of this type of distribution. So we will take up this in this lecture. Also we will take you through some of the applications of the civil engineering problems through these probability models. So our today's lecture is on these probability models using gamma and extreme value distributions. And so we will start with the gamma distribution, where we will first discuss about what are the basics of this distribution function and all. You know that these distributions are discussed earlier in details. Now we will not go into that detail, but we will just briefly overall we will mention those distributions and their few properties, and we will basically this module is focused to its application through this type of probability this type of models. So we will go to some of the examples of this gamma distribution, and there are some problems that we can address through this gamma distribution. Obviously these problems are related to the civil engineering problem that we will discuss. After that we will take another distribution which is extreme value distribution, and we will discuss some of this basic problem first on this extreme value distribution, and we will discuss what are the different types of extreme value distribution. There are basically three types are there. So we will discuss which type is generally is used, and we will also see what are the generalized extreme value distribution form and how we can take those distribution of these different types of information, how those different types of extreme value distribution can be applied to different types of problems. Then we will take that Gumbel distribution, which is also that extreme value type 1 distribution we also say. So this Gumbel distribution having a very wide application, particularly when we are talking about some extreme events in the particularly in the area of the hydrology and water resource, which is one of this discipline of the civil engineering. That we will discuss through what are the different application problems that we can address with this distribution. Also we will see some of the examples using this distribution. And after that, another important distribution is the Weibull distribution. This Weibull distribution generally is used to address some of the structural engineering problem for its failure and all, and we will see, we will discuss that distribution along with some of these problems also. One thing that there is one distribution called the reverse Weibull distribution, which is also that one of this type of this extreme value distribution. This is known as the type 3 distribution. We will see different types, as I told that when we are when we will be discussing this extreme value distribution. So to start with, we will start with this gamma distribution. And we know from the earlier module and our earlier discussion that a random variable x is said to follow the gamma distribution if its probability density function is given by this in this form, which is that fx x equals to 1 by beta power alpha gamma alpha x power alpha minus 1 e power minus x by beta. And you know that the support of this distribution is non-negative, that is greater than equal to 0, that support of this random variable x, and this alpha and beta are non-negative are greater than 0. So far as these are the two parameters of this distribution. And this gamma function, this is a gamma function which is its notation is gamma alpha, and which can be expressed through this one, that is integration from 0 to infinity x power alpha minus 1 e power minus x dx. Now This gamma distribution, this is a PDF, that is probability density function, and the cumulative gamma distribution function is given by, you know, that we have to integrate it from this left extreme, that is 0 to that particular value x, and it will come like this 1 by gamma alpha, which is obviously a constant, and we can integrate this one to get its cumulative distribution. Now, this integration, that is this gamma alpha, this generally available from the standard table. Now, we also discussed earlier that if alpha is an integer, then that alpha that gamma alpha can be expressed as this alpha minus 1 multiplied by gamma alpha minus 1. So, in that way, if we know that these values for the 0 to 1 only for this alpha, then we can get any value of this gamma function for any number. So, that we can get from that table, and this integration we can get from this, either from this gamma distribution table from the standard text or from this numerical integration. Now, there are different softwares that are available from which we can use this we can use the numerical integration to obtain these values. Now, from we have also seen that these parameters, that is the mean of this random variable of which follows this gamma distribution, can be expressed through its parameters. That is, mean is that the product of two parameters alpha and beta, and the variance is alpha beta square. And the other parameters are also discussed earlier. Now, we will see some of this as our main goal of this lecture is to just see how we can use this probability model for different problems of the civil engineering. So, first we will discuss some of the real life problem which can be modeled through this gamma distribution. So, there are, as I told, that this is one of the very important potential distribution because of these two parameters, and most of the cases when we can say that this random variable having a range from 0 to the infinity. So, the negative side is excluded, then the two parameters, that is alpha and beta, are there. By changing their values, it can take a wide range of shape of the distribution. So, so many random variable related to the civil engineering can be modeled through this distribution just by adjusting their parameters. And this we have discussed earlier also. We have shown through the graphical presentation that how this the change of these parameters can change the shape of this shape of the distribution function. So that a wide range of random variable can be modeled through this distribution. So, for details you can refer to the module 3 when we discuss this distribution. So, many real life problems in civil engineering can be modeled through this gamma distribution. For example, that stream flow in a river can be a gamma distributed random variable. So, most of these large river basins where this this stream flow can is always a positive number, 0 to infinity. So, this stream flow can be modeled through this gamma distribution. Again, another most important feature of this gamma distribution that we have also shown in the earlier, that if you just adjust the parameter, this is that exponential distribution is a special case of this gamma distribution. Basically, if we just take that exponential distribution and we can define another random variable which is a summation of those exponential distribution, then that summation is basically a gamma distribution. So, this is what, using this properties, there are many problems can be modeled. So, the gamma distribution can be viewed as a sum of a number of exponentially distributed random variables. Hence, if a construction equipment consists of a number of components whose individual lifespan is described by the exponential distribution, then the life of the total system may be modeled using the gamma distribution. So, there are different components, and each component is having a lifespan of some x1, x2, x3, and all this if all these variables generally can be modeled, you know, that this time to the first occurrence of one event can be modeled through this exponential distribution. So now the full system can be consist of this summation of this distribution. So the total system, the life of the total system can be modeled using this gamma distribution. And another thing is that this is mostly used to address different problems of this transportation engineering, that this gamma distribution can be describe the waiting time until the kth event in a Poisson process. Hence, the time till the kth accident, for example, one example is taken from this transportation engineering, that there are the accidents generally takes place either on the railway or on the highway. So that if we can take that what is the waiting time till that kth accident can take place. So that kth accident take place means there are basically the summation of this k inter-arrival times of the accident. So that it is a summation of those that exponential distribution which is the inter-arrival time is modeled through. This one, so this time till the kth accident, which is a summation of the k individual exponentially distributed random variable. So this can be modeled through the gamma distribution as it is explained in the last point. So we will take a similar problem here. The problem is easy, but it is very interesting to understand that how it is linked to this gamma distribution. So in a particular highway, the inter-arrival time between the successive accident follows an exponential distribution. If on an average an accident occurs in this highway once in 5 months, find the expected time till the third accident. Now, thing is that so this is known, that we know that the exponential distribution that we have described earlier, that and it is given that the average time between the accident is 5 months. So that the parameter of this exponential distribution, which is lambda, is equals to 1 by x bar. So this 1 by 5 months. So this is the parameter for this exponential distribution. Now we have to find out what are the parameter associated parameter for the gamma distribution, and we know that the expected time is looked for. So just the multiplication of the two parameters, that is alpha and beta. So that will give you the expected time for till the third accident. Now the straightforward thing here is that one accident is the 5 months, and we are assuming that these are the independent events, that is the inter-arrival time between the first and between now and the first accident, and then from the first accident to the second, and then from the second to the third. So all these three inter-arrival times are independent to each other. So that if the one inter-arrival time, the expected time is 5 months, then the expected time for the 3 such events can be easily multiplied by this 3 and by this 5 months. So we can get the answer, that is the expected time is the 15 months. Now if we want to convert it from the exponential distribution to the gamma distribution, then the first of all the inter-arrival time between the successive accidents is given by that distribution of this exponential distribution, as it is mentioned in the problem, that is fxx equals to 1 by that is lambda e power lambda x, and this lambda equals to 1 by 5. So 1 by 5 e power minus x by lambda, obviously x is greater than or equal to 0. So if we get this one, then the time till the third accident is described by the sum of the 3 exponential distribution. This 3 means from today. So from today I am starting what is the time till the first accident. This is a one interval, no, it's the one the first incident occurs, then from the first incident to the second incident, then second to the third. So the 3 exponential distributions are there. So the gamma distribution will have the parameters, the x is greater than or equal to 0, and the alpha should be equals to 3 and beta is equals to is 5. So beta is nothing but, you know, that beta is your that 1 by beta is here, that lambda. So this is beta is 5 and there are 3 interval times. So this one, so we have seen that parameters are alpha equals to 3 and beta equals to 5. So the expected time till the third accident is the mean, that is alpha into beta. So 3 into 5, so 15 months, as we are just expecting just by looking the problem itself. So this is how many exponential distribution we are adding, and what is the parameter for the exponential distribution. So that is come from this lambda, and that number of those distributions are being added, from which we are getting this gamma distribution. So we will take another one, another problem. This is also related to the transportation engineering, and sometimes we design the road network for certain traffic volume, and then we can estimate that how is this traffic volume can be modeled through, and this traffic volume also can be modeled through this gamma distribution, and from there we can answer some of the real life problem, that what is the probability of the traffic jam and all. So this type of problem is taken here once. So in a certain highway, the hourly traffic volume is a random variable having gamma distribution with alpha equals to 5 and beta equals to 10. If the hourly traffic volume is greater than the design traffic volume of this 120 vehicles per hour, then a traffic jam is possibly can occur at a crucial junction of the road network. What is the probability that a traffic jam will occur at the crucial junction in a particular hour? So first of all, means traffic jam will occur, that is the random variable that I have to define, that is what is the hourly traffic volume, that is the random variable here, which is a gamma distribution, parameters are given. So now we have to find out what is the probability that particular random variable will be greater than equal to 120. So that is the overall problem is given here. So the hourly traffic volume denoted by this random variable x is given by the gamma distribution with alpha equals to 5 and beta equals to 10. So the distribution that we can get from this gamma distribution, which is that your fx of x equals to 1 by 10 power 5, then gamma 5, and then x power 5 minus 1. So these are just, we are using those parameters, the alpha minus 1 and e power minus x by beta. So we will just put this value here to get that complete form of this gamma distribution. Now the probability that a traffic jam will occur at the crucial junction is in a particular hour is given by this one, that is probability of x greater than 120. Now x greater than 120, you know that by this time that it can be the total probability minus x less than 120, which is 1 minus 0 to 120 of this integration of this full this distribution, and obviously there will be 1 dx. Now if we do this integration, we can use some of the software to do this numerical integration, or we can use some table also to get the value. This value will come as 0.992. So 1 minus 0.992 is give you the 0.00088. So the probability of this traffic jam is very less here, we can see, and this also can be inferred from the data that is given, that is alpha equals to 5 and beta equals to 10. That means the expected time, so the expected traffic volume is that 10 multiplied by 5, so which is a 50 vehicles per hour, and we are looking for the probability which is exceeding 120 vehicles per hour. So the probability that is there so is obviously should be very less, which is 0.008. Okay, now we will go through some of these extreme value distributions, and first of all we will just see what is this extreme value distribution and what are these its possible application. These extreme value distributions are used to model the maximum or minimum limits of a normalized set of independent and identically distributed random variables. So there are some random variables is available to us, and we are interested only for their extremes. The extremes means here either we are interested to know the nature of its maximum side or the nature of its the minimum side. So this when we are interested for this type of variables, that is suppose that one data set is available to me and I am just interested to know it's the maximum one, that maximum value out of this data set, and what is the distribution of the maximum. So that is the extreme value that we are referring to, and its distribution is associated distribution is referred to as this extreme value distribution. Similarly, for the minimum also we will see, and there are different types basically is available that we will discuss through. So, the extreme value distribution, when we are talking about, we are basically referring to the event where out of the set of from this data or out of the set of this random variable, we just want to pick up its one of the extreme, either maximum or the minimum, and want to know its probabilistic distribution. So, if you see from the examples from the civil engineering, one is that for anything, suppose that we are talking about the stream flow, then whether the low flow is the one extreme and the maximum flow is the another extreme. Similarly, if we see that the structural component, so its failure due to the several reasons are there. One of the thing is that fatigue, the failure due to fatigue. So, how many times it can, what is the total time it can go through, what is the maximum time that it can pass through, that can be also be modeled through this extreme value distribution. Similarly, in the other applications also from this environmental engineering or the transportation engineering, whatever the data that we are having, if we are interested to model only its the extreme side, either maximum or the minimum one, then we will refer to this type of distribution. So, some of the extreme value distribution, that is the Gumbel distribution, is one that I was also mentioning at the beginning of this lecture, that this extreme type distributions are widely used to model the peak discharge and minimum daily flow in a stream. And there are other extreme value distribution like the Weibull distribution, which can be used. Basically, this is a reverse Weibull type distribution, which is the type 3 distribution, which can be modeled for this failure of this structure also. So, here we will take that first we will take that generalized extreme value distribution, then we will discuss about its different type, and then we will go through this we will take into details what is this Gumbel distribution, how to model this peak discharge and this minimum flow in a stream. So, this is important because these extreme value distributions means so far as this water resource or hydrology is concerned, we are always interested to know that either the very low flow or the very maximum flow, because both are is needed to be explored for its for the societal impact. So, this we will see. So, that when we are talking about that there is a maximum or minimum limits of a normalized set of this independent and identically distributed random variables. So, we will just see the, first of all we will see what is the specific distribution that we can take you through whatever the knowledge that we have seen from the CDF and the PDF of the if the assumption on the assumption that it is independently and identically distributed. Let us consider a random sample of size n consisting of this x1, x2 and up to xn. And so, this is basically the data that is available to us, and let y be the largest of this sample value. So, we are interested to know the out of this n which one is the maximum. So, that we are denoting as this y. Now, if all the x's are independently and identically distributed, then the CDF of y is given by, that we know from our earlier discussion, is that the CDF, that is the Fy of y, should be the product of their individual cumulative distribution. Now, when we are taking that data set, so each and every observation can be treated as one random variable. So, like that, this is the distribution of this, the first one, that is x1, x2, and this is for the xn. Now, as they are independent, that's why we got their product as to get their joint distribution, and as they are identical, that is, if we just say that all these are identical and equal to that fx, then we can say that fx of, now it is expressed through the y, is power n. So, that there are n different random variables are there. So, power n will give you that CDF of that the largest value of the sample. And obviously, once we get that CDF, we can get its PDF also, probability density function, that by differentiating that. So, this Fy of y is equals to that differentiation with respect to y, which is nothing but n, the cumulative density power n minus 1 multiplied by its PDF of the individual random variables. So, where this f(x)(x) is the CDF of x, that is probability of x less than a specific value of x, and this f small f x x is the PDF of that x. Now, these are all means obviously expressed through that one variable which is y. Now, suppose we will just see the same thing through one example, that is the interval time between two successive earthquakes. So, again we know that these are this can be easily treated as this independent, and this can also be treated as is identical. So, both are so same distribution. If we assume whether we can answer this one, there is a maximum interval time, so the problem related to that one. So, the interval time between two successive earthquakes follows an exponential distribution with a mean of 15 years. So, we know that mean between two successive earthquakes is 15 years, assuming that the time between any two events of the earthquakes are independent of each other. So, this is that first assumption. So, find the probability that the maximum time between two earthquakes exceeds 50 years over a sequence of 10 earthquakes. So, the interval time having a mean of 15 years, we can model it through this exponential distribution. They are independent, so we can get their joint distribution by their product. And then what we are interested to know that what is the maximum interval time, and then what is the probability that the maximum time will exceed 50 years over a sequence of 10 successive earthquakes. So, the interval time, which we can denote by x, follows an exponential distribution with lambda equals to 1 by x bar, that is 1 by 15, and the maximum time between two earthquake, that is denoted by y, follows an extreme value distribution. Now, in a sequence of 10 earthquakes, there are 9 interarrival periods. Now, the probability that the maximum interval time exceeds 50 years over a sequence of 10 successive earthquake is that is Fy of 50 is equals to Fx 50 power 9. So, this is basically we are taking it from that this expression. So, this n is now here total number of interval times, which is 10 minus 1, obviously, that is 9. So, this 9 if we take, and this is that this is their 1 minus e power minus 50 by 0.15, which is equals to 0.72. One correction, this is not the maximum interval time exceeds 50 years. Rather, this 0.72 is the probability of maximum interarrival time be less than 50 years. Now, if we want to know the maximum interarrival time exceeds 50 years, then it should be subtracted from total probability 1. So, the maximum interarrival time exceeds 50 years should be 1 minus 0.72, that is 0.28. Now, we will see that generalized extreme value distribution, that first of all this is a this distribution that we are going to discuss, it is a generalized framework. Now, this generalized extreme value PDF is expressed through a little cumbersome expression, where this Fx is equals to 1 by sigma into 1 plus xi x minus mu by sigma power 1 by xi minus 1. That exponential power, again the same expression, that is minus 1 plus xi x minus mu by sigma whole power minus 1 by xi. Now, if we just see that they are individual element, then it will be more meaningful. That the first thing is that this distribution is its range, its support should be such that 1 plus xi x minus mu by sigma should be greater than 0, where this mu and sigma that we know already, which is similar to our that other distribution, that is mu is your the location parameter and sigma is your scale parameter. Basically both are location parameter means where it is giving the information about its mean, and this is giving its information about its variance. Now this xi is another parameter which is the shape parameter. Now this xi is one of the crucial parameter in this distribution in the sense that it generally controls the tail behavior. Now depending on this whether this tail behavior how it will behave, that we can classify into three different types. The first thing is that if this xi is tending to 0, or whether this is negative or this is positive. So these three cases can lead to three different types of the distribution that we will discuss in a minute. And for this one, if we just follow the same principle of getting its the cumulative distribution function, then it can be shown that this fxx is equals to exponential of minus 1 plus xi x minus mu by sigma power 1 by xi. Now as I was telling that this xi is a shape parameter depending on which it is either tending to 0, or it is positive, or it is negative. So in these three cases there are three different types are there. So this extreme value distributions are asymptotic distribution of the random variable derived from the different parent distribution. Following this extreme value distributions can be categorized into three types. The first type, that is type 1, it refers to the Gumbel distribution. As I was also mentioning earlier, this Gumbel distribution is also known as this type 1 distribution. Here the parent distribution is unbounded towards the extreme values. Now unbounded towards the extreme values means if we are interested, suppose that the maximum one or the largest one if we tell, then we can see that this, for example, that this normal distribution towards the positive extreme is unbounded, and even the gamma distribution towards the positive bound is unbounded, like that. Similarly, type 2, it refers to the Frechet distribution. Here the parent distribution is unbounded towards the extreme values, and the type 3, in this case the parent distribution is bounded towards the extreme values. The extreme value type 3 of the minimum is called the Weibull distribution, which has an upper bound. So with these three types of this distribution, now we will see the one of this, the type 1 distribution, which is the Gumbel distribution. And as I told that this is having a very wide application so far as the hydrology and water resource is concerned, to analyze the extreme values of the stream flow, either it is low flow or it is the high flow. So a random variable is said to follow the Gumbel distribution if its PDF can be expressed as like this, that is fxx is equals to exponential of minus plus x minus beta by alpha minus exponential of minus x minus beta by alpha divided by alpha. This x has a limit from this minus infinity to plus infinity. Now both these signs have some means we have to use one of these sign, as I mentioned, the minus and plus. One for we have to use for the maximum, and other one we have to use for the minimum one. So here it is mentioned that where the minus sign applies for the maximum values and the plus sign is applicable for the minimum values. So if we are interested to model the higher side of the extreme, that is the maximum values, then we have to use this minus sign, and this is then the and if it is for the minimum one, then we have to use the plus sign. Now if we use this transformation, that is y equals to x minus beta by alpha, then the PDF can be again expressed. So this one, just by transforming that x minus beta by alpha is equals to that y. So this PDF can be expressed as exponential of this minus plus y minus exponential of minus plus y. Again that same sign convention, that minus is for the, as I told, the minus is for the maximum and plus is for the minimum. The cumulative distribution function is given by, we can do this integration from this minus infinity to the specific value of this y, and we will get that for the maximum one it comes that exponential of minus exponential of minus y, and for the minimum one it is 1 minus exponential of minus exponential of y. So, even though we started with the complicated or little bit looking cumbersome distribution, but whenever we come to this cumulative distribution, it generally becomes simpler and very easy to remember also. Means this is that f y of this y is equals to, generally we remember it like this, e power minus y, and this is for the maximum. And similarly 1 minus e power y, this is for the minimum. So, you can see that one, that is if we just write that this can be for this minimum one, the minimum one can be written as a 1 minus f of minus y. So, this one is basically for the maximum one. So, generally these tables are available for one of this if it is available only for the maximum also, then also we can use the same table for the minimum through this one, because this if I change this attribute to this minus y, then that one is subtracted from 1 will give you the required value for this minimum one. So, we will see one thing, that is some notes first, that is if the CDF values for the Gumbel distribution for the maximum are available in the standard tables, these tables can be used to obtain the CDF for the minimum also, because as I was telling that f minimum is equals to f maximum, this will be minus y, for this maximum one this will be minus. So, the parameters of the Gumbel distribution as estimated by the method of moments are this alpha beta. So, from this method of moments how it is, so we have not yet so far in this course we have not discussed about this parameter estimation using different methods, as I was mentioned that this parameter estimation will be covered in this module 7. So, till that you can just remember that these are the one of the method of this parameter estimation which is known as this method of moments. So, we will be discuss these things, the different method of this parameter estimation in the next module. So, using that method of moment method, this alpha can be that estimated value of this alpha, this is the parameter of this Gumbel distribution, is equal to s by 1.283, where s is the standard deviation. This beta cap is the x bar minus 0.45 s for this maximum, and x bar plus 0.45 s for the minimum, where this x bar is the mean. So, by knowing if the data is available, we can calculate what is this sample estimate of the standard deviation, sample estimate of the mean, and we can use that those s and x bar information to get that parameter alpha and beta. So, once we know this parameter alpha and beta, we know what is y, and y because is that x minus alpha by beta. So, from there we know what are the probability or what are the particular the question that is asked for. And the mean of this extreme value distribution is given by this beta plus 0.5772 alpha for the maximum one, and beta minus 0.5772 alpha for the minimum one. Variance is given by 1.645 alpha square, and the coefficient of skewness is a constant value for both this maximum and minimum, it is 1.1396. The example of Gumbel distribution, this Gumbel distribution is used in the quality assurance or quality control of the different equipments. This Gumbel distribution has a wide use in describing the yearly maximum daily river flows. Gumbel distribution can be used to model the dynamic pressure of the extreme wind speed. So, these things can be always, means whenever, as I was mentioning, that always whatever the random variable that we are talking about, if we are looking for one of its extreme, then this distribution can be used, and these are the very these are the cases where we have seen in the civil engineering, where the wide application of this distribution is there. Now this one example we will see here, that is use of this Gumbel distribution in defining this mean annual flood. So mean annual flood, the Gumbel distribution may be used to define this mean annual flood. So what is that? The probability of exceedance of this mean stream discharge is given by this probability of y greater than y, which is basically 1 minus probability of y less than y. And this one we know that it is 1 so the exponential of minus y. So this one again we know that this y is equals to x bar minus beta by alpha. So basically what we are looking for is that the mean annual flood, what is its how we can define that. So from the extreme value distribution. So with respect to its return period and all that we will see. So this y is equals to that x bar minus beta by alpha again. So this we know that x bar equals to that beta plus 0.577 alpha, which we have seen from this earlier from the estimate. So that y is equals to your 0.5772. So whatever the this probability we will get, the probability of exceedance, that will, if we put this the value of 0.5772, then we will get what is this, that probability. And if we put in that expression, then it will come that that probability of y greater than this distribution is equals to 1 minus probability of y less than equals to this y, that is the cumulative distribution here. So that is that exponential of minus y, and y in that, as we have seen here, is the distribution for that 0.5772. And if we solve this one, it will see that it is 1 minus 0.5703, which is the 0.4297. Now once we get this probability, what we can define is that what is its return period. So the return period we have seen in this one of this lecture previous to previous lecture, that this is that 1 by p, the 1 by the probability of that particular event. So if we get this one, then we will get the return period of that particular event. That is, so t equals to 1 by p, so 1 by 0.4297 is a 2.33 years. Thus the mean annual flood refers to a flood with the return period of 2.33 years. So that mean annual flood is having a return period of 2.33 years. So this information can be used to find out what is the mean annual flood. We will take one more problem on this, because that is just one of this application that we have shown. That now we will take one example on this Gumbel distribution, where we will see some of this answer for the maximum annual daily discharge. So in a certain stream, the maximum annual daily discharge have an average of this 10,000 meter cube per second and a standard deviation of 4,000 meter cube per second. Now these two information is given, so this can be estimated from this data also. If the data is available, we know this one. Now once we know these two information, then basically what we can get is that the parameters of this Gumbel distribution, just now we have discussed that, so those parameters can be estimated. Now we are supposed to answer that what is the probability that an annual maximum flow will exceed that 15,000 meter cube per second, and second is the what is the maximum flood discharge which has a return period of 20 years. Again, that we know that if the return period is given, we can calculate what is this non-exceedance, what is this exceedance probability, just by getting is 1 by 20. So basically there are the structures of this related to the water resource have some specific return period we have to consider, and based on that we have to find out what is the magnitude of the flood is coming, and with that value we have to use that one, because the whatever the historical data that we are that is available to us may not reflect that complete nature, and for that reason only we have to do this exercise to find out the what is the maximum possible event or maximum possible magnitude that can occur with that return period, and that value we have to this is tremendously useful for this design purpose and all. So one such example is shown here. So the two parameters that we are talking about is obtained from the available data that is recorded for that particular site, and from there I should first model it through the extreme value distribution, and then I will try to find out these answers. So the parameters of these Gumbel distributions can be calculated from this their expression, that is alpha cap equals to s by 1.283, which we have shown just now, that is that method of moments estimated through the method of moments. So this s is now here shown that 4000 divided by 1.283, which is 3117.69, and the beta cap is also that a mean minus 0.45 times of this standard deviation s, and which is a value of 8200. Now so this now what we will get this information on the reduced variable. So we are supposed to know the question that what is the probability that it will exceed the 15,000 meter cube per second. So this 15,000 meter cube per second minus alpha divided by beta, so that should be the reduced variate, that should be the transformation we have to do before we can get that answer. So from this Gumbel distribution, basically to know what is that what is the probability of x greater than 15,000 is equal to what is the probability of y greater than 2.18. So this is why we are just transforming this what is the original data through this x minus alpha by beta. So the probability that that annual maximum flood will be will exceed this 15,000 meter cube per second is given by the probability that y greater than this value is equals to 1 minus this cumulative probability. So this 1 minus exponential of minus exponential y, and just now we have calculated the y is equals to 2.18. So if we put this one in this expression, then we will get this one is 0.893. So the probability that we will get finally is 0.107. So the probability that an annual maximum flow will exceed 15,000 meter cube is 10.7%, we can say. And the second question that was looked for is what is the magnitude here. So earlier we have calculated the probability, here the return period is given. So we are supposed to find out what should be the corresponding magnitude. So here the return period 20 years is given. So first of all we have to find out what is its probability, that is as we have seen in this last problem also, that probability is equals to 1 by t, that is 1 by return period t. So this 1 by t if we put, it is at 0.05. So this is basically that on the right extreme, that is if the distribution looks like this. So basically we are looking for this particular value where this one is your 0.05. So this particular magnitude we want to know from this one. Now it is for the return period t equals to for the 20 years. Now depending on this, what is the project that is under consideration, this can change. So this can change to even 50 years or 100 years or so. So similarly, based on the what is the return period we are considering, based on that this will change. So once this probability we get, but whatever may be this return period, once we get the corresponding probability, then we will be using it from this cumulative distribution and we will get the answer. For example, here the probability is your 0.05, and so this probability of y greater than this magnitude that we are looking for. Obviously, this magnitude first we are looking for in the scale of y. So that is equals to 0.05. So this probability of y less than equals to y is equals to 1 minus probability of y greater than this magnitude. So, or what we can write, that this exponential of minus y, which is equals to 1 minus this 0.05. So, once we do this one, and after this after we solve it for the y, finally we will get the value of this y is equals to 2.97. So, so this probability of y greater than 2.97 is basically this probability 0.05. Now, we have to get it back to the original scale, that is what is the value of this magnitude of this stream flow, which is now is equals to 2.97 multiplied by your that 2.97 multiplied by that value is alpha, or this alpha plus this beta. Basically, this is just the inversion of this expression. So, this if we do, we will get that 17,459.9 meter cube per second. So, we can say that the maximum flood discharge, which has a return period of 20 years, is equals to 17.460 meter cube per second. So, similarly, in the previous problem, what we have seen is that mean flood, flood discharge, mean annual flood, that is having the return period of 2.33 years. So, if we calculate from this data, if we want to know, if we calculate it from here, that what is the magnitude of the return period. So, magnitude of the return period means we have to follow this the first one, magnitude of the return period for the mean value, then we will get that, and then we will first get the probability, then we make it inverse, and we will get that is 2.33 years. Okay, then we will take that Weibull distribution. A random variable is said to follow the Weibull distribution if its PDF can be expressed as this one, that fx x is equals to alpha beta x power beta minus 1 and e power minus alpha x power beta for the x is greater than or equal to 0. And the cumulative distribution function of this Weibull distribution is fx equals to 1 minus e power minus alpha x power beta. So, we will use this one to get this Weibull distribution, and we will see some application in this civil engineering. So, this mean of this distribution is mean equals to this can be expressed through its parameter, there is alpha power minus 1 by beta and gamma of this 1 plus 1 by beta. And variance is also given by this expression, sigma square is equals to alpha power minus 2 by beta, gamma of 1 plus 2 by beta minus gamma of 1 plus 1 by beta whole square. So, with this one, if we just take one example of this Weibull distribution, as I was mentioning that this is generally used for the failure of this structure. So, one such example is taken here through this Weibull distribution. So, this number of cycles before the failure due to fatigue of a steel specimen is a random variable having an Weibull distribution with alpha equals to 0.025 and beta equals to 0.5. Now, I hope that you know this failures due to fatigue means this is there are several experiments also can be referred to. Basically, what does it mean is that it is subject to a reversal of the force, either it is in the compression or it is in the tension. So, this force pattern is getting reversed and a load is applied, which by the static analysis it can be shown that this structure is safe under that load. but once it is go on for this reversal of this force, and there are certain cycle, after certain cycle the structure may fail even though the applied load is within the specified limit. So like that one, so how many cycles it can go through, that can be modeled through this Weibull distribution. And one such example is shown here, for which the parameter alpha equals to 0.25 and beta equals to 0.5. The question is how long can the specimen be expected to last, and so the expected value we have to get, and what is the probability that the specimen will be in operating condition after 4000 cycles. So the first question is straightforward, which is the mean that we are looking for, and this mean we can express is through its parameters. So this mean 0.025 power 1 by 0.5, gamma of 1 plus 1 by 0.5. This gamma value we can get from the table, and we can calculate this mean, and which is the 3200 cycles. So any specimen on an average, that is expected value of the specimen that can last before failure is that 3200 cycles. And the second question is that the probability that the specimen will be in the operating condition after 4000 cycle, and obviously this probability will be less, and so that can be given by this probability that x greater than 4000, and which is the 1 minus the probability of x less than equals to 4000, which we can get from its cumulative distribution function. So this from this on 1 minus e power minus alpha x power beta. So if we put that expression here, so we get the probability is equals to 0.206. So this is the probability that the specimen will be in operating condition after 4000 cycles. So in today's lecture also we have taken some more probability models, gamma distribution, extreme value distribution, Weibull distribution, and in that extreme value we have discussed in detail about this Gumbel distribution and its application to analyze that extreme stream flow values, the annual maximum and all. So we will be taking some more example, because these are all the continuous distribution that we have discussed so far in this module, and we will also discuss that discrete random variable, which are also there are some wide application in the civil engineering, different civil engineering problem, and those distribution we will take in the next lectures. Thank you.